forward. Okay, thank you. All right, so welcome to the February meeting of the Mount Diablo Astronomical Society's general meeting. We have a pretty packed agenda this evening. Before we get going, if anybody needs to use the restroom, they're around the corner here. I want to big shout out to Marianne. We'll have a break midway through. We've got snacks in the back, so thanks to her for doing the snacks every month for us. Do we have any new members in the house tonight? Okay, all right. Well, welcome to the meeting. This is open to the general public, and a suggestion was made to make sure that the Zoom link gets posted publicly, because that has not happened. So we'll make sure that happens for the next meeting. If you have questions, if you could allow me to come around with a microphone, so that the people on Zoom can hear you. People on Zoom, if you have questions, if you don't mind putting them in the chat and ask them, since the audio is not working. Okay. Now my feed is not forwarding. We'll try this one more time. You saw it working. You saw me practicing, right? Yeah. Okay. I'm just going to do it without the... Okay. So just want to mention real quick that we've got the cards for the public astronomy programs for 2024. We've got a ton of them up front. So if you need those for any of your events or to pass them out at outreach events, make sure you grab those before you go. We've got a ton of them. If anybody else needs them, let me know if they leave them for you guys. Okay. Okay, so the agenda tonight, we're going to first have an announcement by our Yosemite coordinator, Renee Gandolfi, really exciting news. And then we're going to talk real quick about star parties, club events. We're going to have our What's Up presentation by Ken tonight by Paul. We're also going to have our Joe Disch Award presentation tonight by Ken. And then we'll have our quick break, 10-minute break, and then we will proceed with our main lecturer for the evening. Okay, so I'm going to stop sharing and I'm going to hand it over to Renee. You can go ahead and screen share, Renee.
Yeah, let's see. Got it?
We've got it.
Okay. And I'll quickly go through a little bit of that history of why many, many years. We're going to have a star party again this summer. For people who have never done the star party, this is sort of the view you get when the sun's still up. When the sun's not up, I can't get a good picture. How are we doing there?
Okay. All right, go ahead, Renee.
Okay, so why don't we have a star party the last couple of years? And if I can get this to do the next slide, which it doesn't want to do. I've lost my technical help here for a sec. Let's see, where am I? So it's a tale of three forces. We have fire. And what happened was in 2018, there was the Ferguson fire. And if you know Yosemite, the road from the valley up to Glacier Point Road was right through there. And they said, nope, we're not going to let you have a star party this summer because there's bad things like fire. Then in 2022, there was the Washburn fire, and you might recognize the Wawona Hotel. It burned around some of the redwood groves and once again beat up the road up to Glacier Point. those two fires combined took out all of the services along Glacier Point Road. In the middle of all that, we had a plague, aka COVID, and the Park Service said, nope, you can't gather a whole bunch of people, so we're not going to have a star party no matter road or not. And then finally, the National Park Service and the Park Service said, well, since the services are all trashed and the roads trash, we're going to redo. And it took them a number of years. They wanted to redo the road because if you've been up to Glacier Point, you know there are some hairy hairpin turns. That's why they're called hairpins. Try to bring a big rig through there. So they've widened some of those. There's another one that they've tried to work on to make it a little bit easier. I'm curious to see what they've done with it. What happens is we set up right here at Glacier Point Amphitheater, and that's the view before sunset. That's us setting up.
Renee, you're not sharing.
I'm not sharing?
No, we're not seeing anything.
You got me. Why it's not?
You're on gallery view.
Can you see this? Can you see this now?
The
Nope.
green button at the bottom?
Nope. All we're seeing is Tara's camera.
Okay.
Where is he?
I thought I had screen share.
No,
We
I'm
only saw the
not.
first
Where
slide.
is
That's it.
Renee even?
So does this share?
There we
Yes,
go.
it's coming.
We're good?
Yep, we're good.
Almost.
Okay. Then I will back up. I probably lost you at a whole bunch of places. So let's come really quickly.
You lost
so
us
let's
in
see.
number 2.
As I said, the roads were kind of trashed up, and they have widened them. This is us setting up at the amphitheater a number of years ago. If quickly, this is an aerial view, and what we do is we come in this road. They let us drive up this dirt road here to dump our equipment here, and then you have to go back and park in the parking lot and then walk back to the equipment. At the end of the night, we're allowed to drive back up here and reload and get out of Dodge for the next night. This is a couple of years ago, and that's one of the cars bringing equipment up. If you haven't been up to the amphitheater, this is the amphitheater. We set up down here. People set up. There is one power tap, I believe, here, but preferably you bring your batteries. Quick explanation of what goes on is that you come up the road, up through Glacier Point Road, come through these hairy hairpins, and we end up there. We camp at Bridevale Creek Campground. This year, because the campground is still under snow, they're not letting us do anything earlier in the year, like in June. So we ended up with a July date. I gave them August dates for better moon, but they gave us July, and that's what we're going to get. This was the road that was trashed, so we couldn't get up there before that. So these are the dates: July 26th, July 27th, Friday and Saturday. This is what nature's going to give us, is a waxing gibbous phase. The moon's going to rise a little bit after 11 o'clock the first night and about 11:30 the second. So we're not going to get really good late night seeing because we're going to have a moon in the way, unfortunately. As I get more information from the Park Service, I will put out an announcement. Anybody can go. I'm just going to need to get your names and get you on the list for the Park Service. Camping at Bridal Veil is gratis of the Park Service. We're up there as volunteers for the Park Service that weekend. We only get Friday and Saturday night. If you want to get up there before or stay later, you have to arrange your own camping. But what I found is if you want to stay after Saturday night, people clear out Sunday and you're still in the campground, so you're first come, first serve. We share campsites. We don't have individual sites. We get one large group site and we make it fit. So I will be delivering more information as something comes, but it's exciting that they're finally going to let us do this.
Definitely, it's really exciting. Do they have a cap on people again?
Still there? Yeah.
Is there any limit on the number of people that can attend?
No, I guess what I would say is if we overload the campsite and we get to the point where we just can't get enough people in, yeah, then there would be a limit. I have never had to limit it before. We've always found a way to make everybody fit. Each campsite has parking for 2 vehicles, maybe 3. If you're going to be hauling up there with a big camper, you're going to use up a lot of our parking space.
All right. All right. Thank you very much for that presentation.
Thank you.
No. So weird. Okay, how do I do this? Okay, I'm gonna just skip my slides because I can't get them to show properly. So next up we have the Joe Disch Award recipient presentation. Joe Disch, this award was inaugurated in 1987. It's the esteemed annual award that recognizes a Mount Diablo Astronomical Society member who has contributed significantly to the growth, development, and camaraderie of our club. I'd like to welcome Ken Coates up to the stage, who was last year's recipient, to announce this year's recipient. And if I could take a picture, Mike.
Okay, so it's been a great honor to be the Joe Disch Award winner for next year. So I really enjoyed the time in my club. I first went across Mount Diablo Society, started the paper and Star Party Mount Diablo. It's quite fun. That was about 2000. Anyway, it's my pleasure to announce this year's winner. And the winner is Dan Van Zangen. My reason I picked Dan was because he's in charge of the membership, which is very important. I paid him all my dues. But he also shows up at the MDAS outreach event. I think it's one of the most important aspects of the club is getting young people excited about cycling. Congratulations, Dan.
Well, I'll just say thank you. I agree with Ken. I mean, it's kind of a pain to be the membership coordinator. All those people who pay right away, I really appreciate that. And there are quite a few, I think we're halfway paid, but for the rest of you, we got a month still, maybe. But I do agree with Ken, the outreach is really fun. We've never done it at the schools or at the top public outreach on that job. Anyway, thank you. Thank you, Karen.
All right, congratulations, Dan. Okay, so next we're going to have Paul Reed come up. He's going to present our 2023 Service Award pin recipients.
Hello. Okay, I'm calling that coordinator, and I think for the sake of brevity, we might wanna, I'll call out the name, hold the applause. Everybody comes up and takes a picture, and then we probably settle up the kids after the meeting. And maybe during the break, just for, continuity. So, Economy outreach is the lifeblood of our club, spreading our love of the Kyle folks to our community, for our commitment to the assistance of many volunteers. And we have a lot of volunteers who have stepped up and made that commitment. On behalf of MDAS, I would like to thank and recognize the following members for their outstanding contributions and commitment to our community and to the MDAS public astronomy outreach program. So, first up, in codes, you guys just come on up and let's stand here and then so be a picture of all. Marty Bernstein, Ken De Silva, Chuck Whitman, Marianne Gannon, Dan Wegnerman, Dave Bellow, Stephen Linda Jacob, Tyler Morrison, John Corlitz, Jerry Frog, Jessica Frog, Louis Mesa, Chris Chastain, Chris Peterson, John Fisk, Pam Howard, Ralph Lambert, Don McNeely, Karen Mustafi, Dave Waldesser, Edwin Walker, Elaine Gandolfi, John Pierre and Andrew Lee, Burrow, Randy John, Rich Lewis, Mike and Marilyn Warren, and myself. Oh, you got it? Yeah.
Anybody need a chair up front? You can all fit between the green amoeba on the wall and the orange guts on the wall. That would be very helpful. Ready? All right, 1, 2, 3. All right, one more. 1, 2, 3. All right, that's great. Thank you. All right.
Okay, who's the doc? Thank you, Paul. Thank you, and everyone.
All right, so we have a 10-minute break for snacks. If you guys are on Zoom, go hit the fridge. Anybody in the room want to come up and interact with Zoom and attendees, feel free. I apologize again for the glitch in the audio. I'll hopefully get that figured out by next time, but come on up and have a chat. So tonight I'd like to introduce our main speaker. This is Claire Gasque from the UC Berkeley Space Science Lab. Claire is a 5th and hopefully final year graduate student at UC Berkeley's physics department. She got her start in research as an undergraduate at Dartmouth College, where she studied Earth's radiation belt and fell in love with space sciences. She currently works at Berkeley Space Science Laboratory, where she analyzes data from large NASA missions, including Parker Solar Probe and the Ionospheric Connections Explorer. She has a very interesting talk. I can't wait to hear what she has to say about our friend Steve and the picket fence. It's not easy being green, unveiling an imposter among the northern lights. Welcome and thank you. Absolutely. Oh, applause before I even start. This is great. So thank you all for having me here tonight. Thank you to the organizers of this, and also thank you all for what you do, engaging the community and, you know, making science accessible and exciting for the folks in this area. That's good, Dave.
Tell me when to stop.
You're good. Okay. Can you all hear me okay, first of all?
Yes.
Awesome, fantastic. All right. So as Tara mentioned, I do work on some big NASA missions, including Parker Solar Probe and the Ionosphere Connection Explorer. Tonight I'm here to talk about neither of those. Instead, I'm here to talk about a pet project that I've been working on with some collaborators for the past year and a half. And it's all about the aurora. Or is it? That's the question. All right. So for the past year and a half, I've been working with some of my colleagues to study something that looks a lot like an aurora, but it's actually something entirely different. And we've been working to try to characterize it, really understand what might be causing these lights in the sky that are not actually an aurora. But in order to understand what isn't an aurora, first let's talk a little bit about what is an aurora. What are the northern lights? How are they created? And to do that, it all starts with the sun, as you all probably know. So from down here, right, the sun looks pretty boring. If you get a sun spotter, you can start to make it look a little bit more interesting. Maybe the solar eclipse, that's interesting too. But when you go out into space, the sun starts to get a little bit more interesting. I think for the folks online, this video is probably pretty laggy, so I apologize for that. The folks in the room, you can see it. Essentially, the sun is constantly emitting this stream of charged particles called the solar wind. Right? These are charged particles, so it's not like the air that we're breathing. The particles have electric charge, which means that they move in magnetic fields and electric fields differently than just the gas that we breathe. The sun is very hot and very dense. The surrounding space is not, right? So there's this constant wind of particles that's actually coming off the sun, streaming towards Earth. It's moving extremely quickly. It's about 300 miles per second. So to contextualize that, right, if you were going back to the East Coast to visit your family, it would take you about 10 seconds to get there if you were the solar wind. Or you could get to Los Angeles in like 1 second. That'd be great, right? Luckily for the Earth, as you can kind of see in this video, the Earth has a magnetic field. And these particles are deflected by the magnetic field, so they're not constantly bombarding the surface of the Earth. Other planets don't have as strong of a magnetic field, so the solar wind actually affects them a lot more. But luckily for us, we have a relatively strong magnetic field, and so it creates this kind of cavity around the Earth. So that's what's happening when the quiet solar wind is hitting us. But sometimes the sun is a little bit more eventful. This is a coronagraph image, right? So the sun is behind that little spot in the center, which is covering the brightest part of the sun. So you can actually see the sun's outer atmosphere. And this is a coronal mass ejection. So this is what happens sometimes. The sun just spits a lot of material, much denser, much faster than that normal solar wind. And when that happens, so the sun is going to emit a coronal mass ejection. If it happens to be in the direction of the Earth, that's going to race towards the Earth. It takes a couple days to get there. It's going to hit Earth's magnetic field and actually cause it to break in the front. It wraps around, squeezes our magnetic field in the back, energizes particles, those stream down the magnetic field lines, and that's one of the ways that you can create the aurora. We'll just play this again because I know that was a lot of information very quickly. Right? So you have an explosion on the surface of the sun, the particles stream towards the Earth, they hit Earth's magnetic field and actually break the field lines. Those wrap around, and then different field lines are going to reconnect in the back, and that releases a ton of energy. Particles get energized, these are still charged particles, stream down, creates the aurora. This is a video of what the aurora looks like from space. Oh, by the way, if you have questions throughout, feel free to stop me. Yeah, I think I saw him.
Okay, so I've read this before, and I think I looked it up at least once or twice. You see charged particles, photons, electrons, what kind of charged particles?
In the solar wind?
Yes, in solar wind.
Solar wind is primarily protons and electrons.
In the Earth, in the ionosphere, we also have charged particles. Those tend to be heavier species. So that's normal air that loses a charge and gets ionized. That's like electrons and oxygen ions, for example. But yeah, solar winds, mostly proton collisions. Yeah. Any other questions while we're here? I know that it's a lot with the aurora. There's a lot going on. Okay. This video is actually taken from the International Space Station. This is the aurora from space. And so just to emphasize, right, the aurora, it's these shimmering curtains of light that you see in the sky. That's, I think, one of the solar panels from the ISS. Not aliens, I promise. But in general, the thing to emphasize with actual aurora is that it's particles that are energized hundreds or thousands of miles above the atmosphere. They're getting energized out there by various processes, and then they fall into the atmosphere. And what's happening is when they hit the air in Earth's upper atmosphere, they essentially heat it up, right? They're knocking it into an excited state. And then when it cools back down, or when it falls back into its ground state, that's when it's releasing the light that you see as part of the aurora. So these lights are kind of tracing where those charged particles are hitting the atmosphere in the aurora. But again, the particles are coming in from very far away. So that gives us our working definition of what is an aurora. I looked it up in the dictionary. That's what you do when you're trying to do a PhD. So, according to Merriam-Webster, an aurora is a luminous phenomenon consisting of streamers or arches of light appearing in the upper atmosphere of a planet's magnetic polar regions, caused by the emission of light from atoms excited by electrons accelerated along the planet's magnetic field lines. In plain language for us, right, it's bands of light in the sky, usually near the northern or southern poles, created when high energy particles accelerated in space collide with the atmosphere. Fun fact, right, Earth is not the only planet where we have observed auroras. Theoretically, for any planet that has a magnetic field, the particles could be accelerated along those magnetic field lines to the atmosphere to create aurora. We have pictures, I think these are all from the Hubble Space Telescope, of aurora on Saturn and Jupiter and Uranus. Uranus is kind of funny because it actually doesn't have the same kind of nice magnetic field that the Earth does, but rather it's a much more, I guess you'd say, random configuration. It's not as dipolar as the Earth. And so you get aurora in really weird places, basically. It's similar on Mars, so you can get aurora in some weird places. But Saturn and Jupiter, the magnetic field looks a lot more like Earth, and you do get it primarily in those polar regions. All right. So there's lots of different types of aurora. There's lots of different shapes. The shapes are mostly based on where those particles are hitting the atmosphere, so they're kind of defined way out in space. The color is based on the energy of the particles that's coming in, and also the composition of the atmosphere. Showing these pictures, I'm not being entirely truthful, and this is going to be a bit of a test of who reads the newsletter. Because one of these is an imposter. So I'm gonna actually have us take a vote, which might just reveal who reads the newsletter, because the picture wasn't there. But one of these is not truly an aurora. If you think that aurora A is not the real aurora, let's get a show of hands. All right. How about aurora B? All right, there's a couple tentative aurora Bs. Aurora C. Anyone think that's not the true aurora? Okay, a few. And aurora D. Okay, I feel like everybody realized that the people who said A are the ones that read the newsletter, right? Yes, aurora A is the imposter aurora. So allow me to introduce you to Steve. This is real. This is actually what we call it. It is named Steve. There is a backstory here. So Steve and the picket fence, first of all, they only made it to the scientific literature in 2018. So this is relatively new in terms of us trying to figure out what this actually is. And it was actually first discovered by citizen scientists. So folks for whom science is not their day job necessarily. Who in this case are aurora chasers, is what they call themselves collectively. They go out into their backyard or farther afield with a camera, and they document the aurora. They take beautiful pictures. Scientists, we've been trying to actually work more and more with these citizen scientists who have a much further reach than what we can do to try to identify some of these interesting phenomena. This is a great example of how that citizen science community and the scientific community have worked together to discover something new. But yeah, so Steve was first discovered by citizen scientists, and I will tell you the story of the name. So this was discovered by someone who presumably had a child, and they recently watched a movie called Over the Hedge. Don't know if any of you have seen it. If you are between the ages of 20 and 30 or have a child between the ages of 20 and 30, there's a good chance that you asked. But this is a story about a ton of woodland creatures, I guess like the ones in this room, who are exploring their wilderness, and one day they come across a big hedge. And this is like something they've never seen before. They don't know what to call it, but they need a name for it so they can discuss amongst themselves. And the squirrel says, let's call it Steve. Perhaps you can see the connection, right? This big thing in the sky, we don't know what it is, but we need a name for it, so we need to describe it, so we called it Steve. Steve is the purple band that you see up there, purple, white, mauve, those kind of colors. Beneath it, we also have the picket fence, which are those green streaks of light in that alternating pattern. Again, this first came to the attention of the scientific community only in 2018. The very first paper talking about it really called out the citizen scientists as the ones who discovered it. And in the very first paper that came out that was describing it, they actually had a satellite that flew over Steve at the same time as the pictures were taken from the ground. I'll try not to show too many thoughts in this because I know some of you are kind of far away. But in general, what this is showing, the top one is showing the intensity of the light. So you can really see where the intensity of the light is going up, that's where the Steve is happening. And at the same time, it's showing that this is the flow of charged particles up where the satellite is at about 400 kilometers up. And you can see right where the light is, there's this really extremely fast flow of charged particles. So this is at about 5 kilometers per second. So again, per second, very fast. And at the same time, they didn't see any of those particles falling down from space the way that we have when we get the aurora, which hinted that this was something entirely different. The astronomers therefore called, or the scientists called it the strong thermal emission velocity enhancement. So that's what we call it. As an homage to the original citizen scientists who discovered and named this, we now call it Steve, but it's all caps, it's different, it's scientific. Right. And so when it comes to Steve, we didn't quite what made it. We thought that those fast flowing ions might have something to do with it. But actually, we're still not quite sure. The way that we got closer to understanding what it was by looking at the spectrum. If you all are an astronomical society, I assume that a few of you are familiar with the concept of spectra. Yes, we're getting some nods, some people aren't moving their heads, so I'll just explain it anyway. So see, right, it's this purplish color. That's what it looks like to the naked eye. It's stretching east-west across the sky in general. Sometimes it has these green picket fences under it. Sometimes it doesn't. Sometimes the picket fence is alone. But when we want to look at the spectrum, right? So what we're talking about is the electromagnetic spectrum. In general, we're going to be looking at the visible light portion because Steve and the picket fence appear as visible light in the sky. But if you're looking at the electromagnetic spectrum, right, we're looking at different wavelengths. In general, if you're looking at radio waves, those are about the size of buildings, right? You can get down to microwaves, which are like the size of a fly, about this big. When we're talking about the visible light, we're talking about wavelengths that are about the size of a bacteria, that sort of thing. And then you can get down to even shorter wavelengths, looking at ultraviolet, X-ray, gamma ray, which are tinier and tinier. But here we're going to be looking at visible light. When we're just looking at a normal green aurora, which is the most common color of aurora, this is what it looks like. So here to orient you, right, we have the wavelength of the light on the bottom here, or conveniently a rainbow, in case we don't care about the actual numbers of the wavelength of the light, and then the brightness of the luminosity is here on the y-axis. The biggest thing that you see in green aurora is you have this line just right in the green part of the spectrum, which is created by atomic oxygen. When it gets excited, that's the dominant feature. That's why the aurora is going to look green to your eye. There's a couple of other things hiding in here as well. There's some red, which is also from atomic oxygen. There is some red up here, these little band structures, which are from nitrogen. And then down here in the short wavelengths, there is some blue, which is also created by the ionization of nitrogen. This is going to be important later, so remember this blue. But for now, when we're looking at Steve, it actually looks entirely different. This is what Steve looks like. Yeah, exactly. That's what we said when we saw it. So in Steve, right, first of all, the brightness is a lot less than what we're seeing for the normal aurora. Although you can have brighter or less bright Steve, this is an average of a bunch of Steve spectra together. You have a little bit of that green from oxygen, although it's not super significant above the background levels. You have some of the red line from oxygen as well. But in general, what you have is above this 0 brightness, right? You kind of have all of the colors. Basically, there's a continuum of light across all of the wavelengths, which is why it looks more white or purplish. And we have no idea what makes this, right? We can look at these bands of the oxygen and be like, okay, you know, this is the transition, it creates this wavelength, we know what that is. When it comes to this continuum, we're not really sure what it is. It's nothing that we are aware of in the aurora. There are no processes in the aurora that we know of that can create this. So this seems entirely different. There are some theories out there in terms of what is creating this. The only really current viable theory for this emission was actually written by a colleague of mine, Brian Harding, who's also at the Space Sciences Lab. His idea was that those fast-flowing ions that we observed with Steve with the satellite are going to collide with nitrogen, and it's a reaction that then creates nitric oxide, and that could combine with oxygen, and that will create NO2 and spectrally broad light. That was the idea. He modeled it out. It kind of works, but not quite. It doesn't quite explain everything. So this is, again, the spectrum of Steve, the continuum you can see there. And then based on this idea, the black line is the spectrum that would be created, and it kind of matches, except not really down here. So if you cover that part of the graph, well, okay, we can't do that as scientists, so maybe not. The other thing is that this theory predicts that Steve should be very smooth, but recent high-resolution imaging reveals there's actually a lot of substructure in Steve. So this is what it looks like. You can see that there are some bands of brighter or less bright light. And that substructure cannot be explained by this theory either. So honestly, the origin of Steve is still an open question. We're still not sure about this. It's not thought to be created by auroral particle precipitation, but the actual origin is still a mystery. That's the last thing I'm going to say about Steve, although you're welcome to ask questions at the end. But now the question is, what about the picket fence? Okay, picket fence is green, normal aurora is green. Great, there's a connection there. Maybe it's the same as normal aurora, right? That's actually what people thought in the beginning. This is an early paper back from 2019. And at the end there, if you can see it, they say, yeah, so we suggest that electron precipitation is driving the picket fence, just like aurora. And they say, okay, and then heating is maybe the Steve part. But they're saying, yeah, it's probably electron precipitation for the picket fence. And that's because the color looks similar, and some observations suggested that that might be the case. But to look at this, we need to look back at the spectrum. So just to remind you, this is the normal green auroral spectrum. Again, right? We have mostly green, a little bit of this red, some of this red, and this blue. Each of these has a different amount of energy that it takes to make it. The red line, this only takes about, well, I'll use unit, about 2 electron volts. The green line takes about 4, this red takes about 7, this blue takes about 18. In order for electrons that are accelerated out in space to get down to the altitude of the picket fence, they need to have like a couple hundred eV to get there, which means that they're going to make that blue. Like, it's just going to happen. But then when we look at the picket fence, there's no blue. Right? Where's the blue? So the picket fence, it is predominantly that same green that makes the green of the green aurora. It's from atomic oxygen. There is a hint of this red from nitrogen, You don't have any of the red line from oxygen, but we actually expect this because the picket fence is a little bit lower. And down there, you don't get the red from nitrogen as much. But not having this blue is very suspicious. And that suggests that it can't be particle precipitation that is creating the picket fence. So in summary, when you have particles raining down from space, you're going to get some blue light. We don't have any blue light, so it's not created by particles raining down from space, which makes it an imposter. There's that. So Steve, we think that both Steve and the picket fence are imposter aurora. But then, okay, so the question becomes, if it's not an aurora, what is it? What causes it? There has to be, there has to be some way to get this light. What is it? Essentially, we need energetic particles there with enough energy to make the green and the red from nitrogen, but not enough to make that blue from nitrogen. So we're constrained to particles that have energies between 7 and 18 electron volts. Somehow we need to get that population. And if we can't energize them out in space, because then they wouldn't be able to get down there, the question is, how do we do it? And so our idea is that, okay, instead of being energized far away, right, then they couldn't make it to where the picket fence is, maybe the charged particles are getting their energy right there where we are seeing the light. So right in space, about 100 kilometers above us. Our idea is that they might be energized by parallel electric fields. So electric fields are essentially, like what drive current in a wire. The idea is that if you have electric fields parallel to Earth's magnetic field, you can accelerate particles right where those electric fields are, maybe to the correct energies. That's what we're going to test. And then those could collide with the atmosphere right there and create some light. That's the idea. Question in the back. What was that question?
Well, it sounds like from what you're saying, it's like maybe we're creating that energy through our response with all the ones going on maybe in the world.
That's an interesting idea. I think that, so you can get electric fields naturally in nature, and you do frequently. Essentially, once you get up to a certain altitude, you have a lot of charged particles, you have magnetic fields. The way they move and the way they separate, that can create electric and magnetic fields on its own. I think there's an analogy to what we do, but I think that this would be naturally created. If you went up there and
So from the Earth, maybe naturally.
Yeah. Another question over there?
So I understand that the Earth's magnetic field has been losing strength since like 1859, the Carrington event, right? So it's down like 15–20%, which theoretically would allow more of the protons and electrons to funnel into the cold from the sun, right? Which then potentially you could have radiating up, because the Earth is like a capacitor, right? It's going to radiate up that energy that it's beginning to accumulate in the weakened electric field. It's possible that is radiating up from the ground, similar to what you see when you see the electrical above earthquakes, right? Where the atmosphere becomes hypercharged. Is there potentially another Earth phenomena coming up? It's now showing up because of the decrease in the electrical or the magnetic field.
That's a good question. I think it's unlikely based on what we know. First of all, even though these only appeared in 2018 in the scientific literature, we've actually looked at the scientific record, and these appear all the way back to the 1800s and before. So even though it's new in the scientific literature, it's not new in nature. It's just that we hadn't identified it as a new thing. On top of that, these tend to happen more during magnetically disturbed times. So when something weird is happening in the sun that is disturbing Earth's magnetic field as a result of that, there's a strong correlation between those times and when we see those, which leads us to believe that there's something more to do with what's happening deep in space and how that's changing Earth's magnetic field versus something on the ground.
And I think you have a chat question.
Okay.
Can you hear me now? Okay. There's a chat question that says, could some human agency conduct experiments with high energy particles we might not know about? Or the floor confused? There's some human agency, I guess, rather than.
Yeah, also a good question. As far as I'm aware, again, these are strongly correlated with when there's something weird going on in the sun with the magnetic field. So it's likely that these are natural. There are experiments, like there's one in Alaska, which is called HARP, where they send electromagnetic fields out into space. And those actually can create emissions that may or may not be similar to this. We actually haven't fully done that experiment yet. But again, these are thousands of kilometers east-west across the sky. And again, they're highly correlated with things that are going on out in deep space. So it is likely that these are natural. Another question.
Hi. Could you mentioned the things happening in deep space. Could you describe some of those and how they would affect the Earth magnetic field?
Sure. It's kind of like that movie that I showed very early on when there was a coronal mass ejection and that was causing the magnetic field to either break or just bend. Those types of disturbances, right, where there's pressure from the sun impinging on the magnetic field and causing it to vary more than it would just under quiet conditions. That's kind of what I'm talking about. Does that make sense?
Yeah. Thank you.
Thanks. All right. There's more chat.
You got us rolling.
Person asked, sorry if I missed this, but where do these occur on your northern latitude?
That's a good question, and I think I forgot to mention it, so thank you for asking. So these occur at sub-auroral latitudes. So the aurora typically happens, think northern Canada, this happens southern Canada, more or less. During magnetically disturbed times, as I'm sure you've seen, like the aurora can come further south. Theoretically, these could come further south as well during times like that. But in general, they are closer to us than the aurora is, but they're still pretty far north.
Was this only observed in the northern latitude, or was it also in southern latitude?
It has predominantly been observed in the north, but that's mostly because there are more people in the north. There are one or two observations of it in the south, but in general, there's much less land mass at those latitudes in the south, which means that we're heavily northern biased.
Yeah.
Yeah, good question though. Okay, shall we continue? Okay, so there's the hypothesis, right? Maybe we're getting those particles energized right there instead of far out in space. Maybe parallel electric fields are doing it. So we set out to test that. This is actually what's called a keogram. So on the y-axis, this is where we're looking on the sky. So it's just the elevation angle where 90 degrees is straight up. That's time there on the x-axis. So at different times in the night. And so basically what this is showing is that we have how much green brightness do we get at a certain spot on the sky over time. And here we saw a couple examples. These are where the green brightness is particularly bright. And these are examples of picket fences that we observed. Each one of these points, we actually have an entire spectrum for. So we were able to take this and get a bunch of spectra to try to understand what is the range of those spectral features that we're seeing. And then can we use that to do some modeling based on our hypothesis? What we found from this is that we have the green line. That's how bright the green line is on the x-axis. We have how bright that red that we saw, the red from nitrogen is on the y-axis. And we found a pretty steady relationship between those two. So there's a pretty steady ratio between how much green light there is and how much red light. And again, there is no blue light. So that's what we were going to try to recreate with a model. can we create this ratio between those two colors of light while creating none of the blue light? So this might get a little complicated, but I'll try. But essentially what we did was we took a model of the upper atmosphere, right there. We have electrons, we have ions, and we have neutral air, just like what we breathe, and it's all right there. So we have this, and in a computer model, we put an electric field in there, and we looked at how that changed the energy in the electrons. They are constantly colliding with the neutral gas, just like what we're breathing. They're colliding with those, that's going to change their energy, and that's also going to create some light. The important thing here, this is actually looking at the energy distribution of those electrons. The y-axis here, it's kind of just the probability that an electron will have a certain energy, and the energy is here on the x-axis. So these black lines are if we're applying stronger and stronger electric fields. And so the idea is if we have a relatively weak electric field, right, all of the electrons are below like 2 electron volts, that's not enough to make any light. That's the idea. As you're cranking up that electric field, the tail of this energy distribution function is stretching to higher and higher energies. That just means that you have some electrons at higher and higher energies. At the same time on this graph, I've put, these are sort of the cross sections for when you're gonna get the light. So at green, right, it starts at about 4. So here you'll start to get green light, which means, right, if you have 20 millivolts per meter, you won't get any green. If you have 60, you're gonna start to get some green. And you're gonna start to get a tiny bit of red. Whereas at 115, you'll get some green, some red, it'll be a different ratio. When you crank it up to 170, you might actually start to get some of this blue out here, right? So that can create a natural constraint for us for how big of an electric field you would need to create the light that we're seeing. And we can actually test whether we can actually get something that matches that exact ratio while not getting any blue. That was the idea. Right. And what we found was that actually we can recreate the exact spectrum of the picket fence using parallel electric fields. This is looking at parallel electric field strength on the x-axis. This is actually the altitude in a realistic atmosphere. That observed ratio, which was 0.34, appears right here on this plot. The picket fence tends to happen at about 110 kilometers, which means that we can look here and be like, okay, so we need about 100 millivolts per meter parallel electric field in order to create the picket fence. And we can do it. We can create the same ratio between the green and the red light and get none of the blue light with this mechanism. That's the idea. So our hypothesis might be correct. I guess let me pause there and see if anyone has any questions about this, because this was kind of a lot, maybe. Okay, you all understand it perfectly. That's
I know the cosmic rays also. Cosmic rays?
That's a good question. When it comes to Earth's ionosphere, cosmic rays are few and far between. So they wouldn't be able to do the same kind of broad, very large feature of brightness that you would see here. They also tend to produce much higher energies than the visible light you're seeing here. So think more like X-rays, those types of things. So probably not, but good idea. In the back?
Does your model predict any lower frequency light, say like infrared, and do we have any observations or data?
That's also a good question. One thing we looked at was actually the other side of that. We looked at what ultraviolet emissions would be predicted, and we have some predictions for that. When it comes to the lower frequencies, there's going to be more of that actually nitrogen red that extends deep into the infrared. To my knowledge, there are no observations of this current. So that's a good question. Anything else? Okay. So then, I've done this whole thing. It's not an aurora, it's something else. This might be what causing it. Question is, why does it matter what we call it, right? It lights in the sky, aurora lights in the sky, it's fine, right? It's fine. So here's the thing. When we're looking at the aurora from a scientific perspective, scientists actually use it to try to trace what's happening way out in Earth's magnetic field. And the problem is, if some of that light actually isn't made that way, that doesn't work anymore. And we have to reassess our models and try to really understand what's going on. Because otherwise we don't quite understand the connection between the deep magnetic field and our atmosphere. So from a scientific perspective, that's why it matters. And actually there's some other imposters out there. Also, these are actually within what are, the normal aurora. So the normal region where you see aurora. There are these which are called fragmented aurora-like emissions. If you look at it, this is the only picture I could find is from a paper that came out in 2021. It looks a lot like the picket fence, but it's actually on the poleward side of the aurora rather than on the equatorward side like the picket fence. So it's in a completely different area. And this one, if you look at the spectrum, it has the exact same thing, right? There's the green, there's the red, there's no blue. Same.
The folate?
I think they call it just FAE, and they get rid of the L.
No.
But yes, there are acronyms for everything. That's a good point. We do acronyms for everything. You have an acronym too, so you're one to talk. Sorry. Another imposter, we have what's called the enhanced aurora. So on the left here, this is the regular aurora. You kind of have a smooth curtain of brightness. It's dimmer, it gets brighter towards the bottom, and it's just very continuous. On the right, this is what's called the enhanced aurora, where you can see it slowly getting brighter, but then it suddenly gets a lot brighter, and there's kind of this discontinuity in the brightness. And that part at the bottom, which is much brighter than the top, actually has the same thing, where there's a lot more green and red compared to blue. There's still a little bit of blue because there is precipitation underneath here, but the ratio changes dramatically in that part. Hence, there's another imposter hiding in the normal aurora. And this might happen in as many as half of the aurora that we see, which means this might be an important thing from an energy perspective when we're looking at this. And so what we want to do is try to measure whether there are electric fields here. So last fall, actually, we proposed to NASA to send a rocket through the enhanced aurora to try to measure those parallel electric fields for the first time. The theory says that they might be there, right? And it says that the spectrum is consistent, but no one's actually measured these and we haven't actually seen them. And so we're going to see if NASA will let us send a rocket through the aurora. The enhanced aurora happens a lot more than Steve and the picket fence, which is why we're starting with that to see if we can measure it, do a proof of concept, and then we would hopefully move on to do a Steve and the picket fence rocket to really get measurements inside Steve and the picket fence for the first time. Also, there is still a lot of unanswered questions about Steve and picket fence. This has only been in the scientific literature since 2018. It's relatively new. There's still a lot that we don't know. It includes, what causes that structure in the picket fence? We're not sure. How are Steve and the picket fence related? Sometimes Steve is alone, sometimes the picket fence is alone. Most often they're seen together. It seems like some of the substructures might be connected, but we really don't know why. What causes Steve's purplish-white color? As I said earlier, there's some theories, but they're not quite able to explain everything that we see with Steve and the picket fence. So this is still a very open area. But that is it for me for tonight. If you are interested and very scientifically minded and don't mind jargon, this is actually the paper that the presentation is based on, which you can scan the QR code. I'm happy to, if you want to email me after, that's fine too. But for now, thank you very much for your attention tonight, and I'm happy to take questions.
I'm just wondering, is there like a plasma wind type of event thing going on with the
So up where Steve is, there are those very fast ion flows, which is essentially what you're talking about. It's kind of a plasma wind or a plasma drift. Those are probably up a little bit higher than where we're seeing the picket fence, but they're likely related to what we're seeing in Steve itself.
Yeah, well, the reason why I asked is because we can pick up mentions and everything. The Earth's weather is generated by differential heating and storage. Then you get all these weird fluid dynamic effects like cloud streets, which is, the leading things that you see. So I'm just wondering if there's some kind of disturbance of fluid dynamics that's going on that altitude with like an emission type of velocity.
Very possibly, yeah. It's there are likely instabilities in the plasma there, which would create something similar to that. If it is the parallel electric fields that are creating the light, then whatever structure you're seeing in the picket fence is structure that would be in the electric field itself. So it would be on, off in terms of the electric field. But you're right that it could be some sort of instability process, somewhat similar to what you see in clouds and earth weather that could be doing this. So yeah, good idea.
This is gonna seem kind of weird, but in doing this research, what value does it have for humans on our planet and here for Earth?
That's a good question. Probably should have put that in the why does it matter slide, right? Because maybe, yeah. So here's the thing, the ionosphere is kind of the transition region between our lower atmosphere and deep space. That's the area that essentially like GPS signals are going through it. Most of our low Earth orbiting satellites live in the ionosphere. With the proliferation of low Earth satellites like the Starlink constellations and other things like that, a lot of our infrastructure is moving to space, and it's living right where this is living, essentially. And there's still a lot of things that we don't understand about the weather in space and how that can affect things. If you remember, I think it was earlier, like 2023 maybe, there was that event where all of the Starlink satellites were lost. That was because there was a geomagnetic storm and we couldn't fully predict what that would do to the satellites, and they weren't able to account for that, and so the satellites burned up in the atmosphere, essentially. So this type of research, understanding how energy moves through the system, how the system works as a whole, is important for safeguarding the future of our space infrastructure, if you will. The picket fence itself is essentially a signature of really extreme energy inputs into this environment. So it's kind of what happens on the extreme. And we can use the light as a diagnostic for what's going on in the plasma. That's what we're trying to do. Does that answer your question? Okay, thanks.
Good work, by the way. I'm wondering if you think that what you've explained might be related to strikes and sprites. You know what those are? I mean, I know they're very different phenomena. But I don't think strikes and sprites have been explained that well yet. I'm not up on the current research, but I mean, like I said, the strikes and sprites, they discharge very quickly, right? As opposed to these things that last a long time.
Yeah, absolutely. So for those who don't know, there is something called transient luminous events, or TLE, another acronym. These are, it's kind of like lightning is an example of it, right? A sudden flash of light. Things like sprites and elves and those things actually happen above thunderstorms. You'll see like this branching red light above thunderstorms, or it'll sometimes be blue, depending on what species of TLE you're looking at. Those actually are somewhat related to this. Those are created also by those electric fields, similar to the way lightning is. Lightning is a big discharge from an electric field. The difference is that up here, the atmosphere is very different. It's a lot thinner. And you also have charged particles up here just floating around kind of normally. Whereas down there, the charged particles are like lightning creates plasma, for instance, but it doesn't stick around for very long because the atmosphere is so dense. In doing this work, we actually borrowed a lot from the TLE community in terms of the modeling. And the second author on this paper works primarily with sprites. So seeing that connection was is interesting.
Real quickly,
Yeah.
I understand that some of the strikes and sprites, they discharge up to like 500 kilometers, something like that.
Maybe. I'm actually not an expert in that community, so I'm not sure.
That's what I've read.
My understanding is that they predominantly happen between like 60 and 80, but it's possible that they could reach that high. I'm not sure. Thanks.
My question actually doesn't have to do with the aurora, but on the clip that you showed with the space station, and showing the Earth, in the upper right-hand corner, I believe it was like a comet. You know what comet that was?
Short answer is no. But shall we go look for it? We can go look for it. I'm gonna commit the cardinal sin of PowerPoint right now. Just scroll backwards through everything. Oh my God, here it is.
That's there.
Where are we
There's a
looking?
comment right there. Is that it? Up above. Yeah. So it's to the left of it.
That's what we're
Right
looking
there, yeah.
So here's the thing, right? I don't know, it doesn't seem to be moving as quickly as the background star.
Right,
It looks
right.
like a reflection off of something to do with spacecraft to me, or something to do with the lens.
It could be. It could be.
I don't even know.
Could it be the larger, small magellanic cloud? I don't know.
I think this is just either a lens or a spacecraft effect. I don't think it's real.
Could be.
But good spotting. I was just staring at the aurora.
Yeah.
Yeah, of course.
It's another Steve something or other.
Yeah, you discovered the next Steve.
Yeah.
Maybe.
The peas, yeah.
Going around for another question.
Periodical electron.
All right, this is the next step, is to put a rocket up there, but would it be helpful to have instrumentation on the Starlink satellites that's there in the environment?
That's also a good question. So the Starlink satellites are actually in orbits that kind of exclude the polar regions for the most part. They probably
Type of satellites on a public road.
on a polar orbit would be better. So the thing is that, so Steve and the picket fence itself is happening, like I said, at about 110 kilometers. Steve is a little bit higher, maybe around 270. Most low Earth orbiting satellites are at a minimum of like 400. The thing is, the lower down you get, the denser it gets, the quicker drag is gonna just annihilate your satellite.
Take your orbit.
When it comes to sampling specifically that region of space, you really need a rocket. You can send up a balloon, but it won't get high enough. A rocket will go through it and the satellite can't get low enough. So really you can only take remote measurements. The advantage to measuring in space would be that you could measure the ultraviolet light a lot better, because from the ground, the atmosphere blocks a lot of the ultraviolet light. But in terms of like, if you actually wanted to make a measurement of, you know, the atmospheric composition or those electric fields right where this is happening, you really need a rocket to do it.
That's like a second question. So that if you had a satellite that was looking down on it.
So from that, again, you could take ultraviolet is the immediate thing that comes to mind. That would be the advantage of a satellite there. You can also take measurements like from that first plot that I showed of a satellite flying over, where you can look at how fast the plasma is moving. You can look at changes in the magnetic field, which might indicate something's going on. But for electric fields, there's not a good way to sense them from far away. You really need to be right there in order to understand what's going on for those.
Yeah, there's a quick question about, since you're driving the eclipse, how does the moon eclipse the sun affect the solar?
It should not have a large effect.
And the second question is, how protected, so we're sending people back to the moon, how protected are people on the moon from these normal mass ejections?
Probably not like
That's
we are.
not very well, honestly. So the moon actually, if we go back to not this one, this video, right?
Yeah.
You can see that cavity where the magnetic field is
Yeah.
protecting.
It's-
Sometimes, so the moon is not in here,
Right.
first of all. Sometimes the moon is inside the magnetic field, sometimes it is outside. When it is inside, it has some of the benefits that Earth does, but not quite as much, because it's still kind of in Earth's radiation environment, which is its own thing.
Yeah.
But when it passes outside, then it is essentially unprotected from the solar wind, because the moon does not have a strong intrinsic magnetic field at all. Which means that it is constantly being bombarded by this. Things are being ionized, stuff is being thrown around. As a person who wants to live, it's not the best place to be.
Nope.
Unless you have significant shielding from radiation or some other solution, or we cure cancer, you know, that could do it too. But I don't work on that, so I don't.
So where geographically do you need to be to launch a rocket into the Steve phenomenon? Like, would it have to be a polar launch pad? Like,
What are the logistics of that?
So steep is actually hard, so the Aurora is easier than steep. There are some launch pads that are pretty far north. There's one near Fairbanks, Alaska, in Poker Flat. They also have one in Andøya, Norway, where they often do these types of missions from. That's actually not too hard. When it comes to steep and the picket fence, it's actually harder because at those latitudes, a lot more people tend to live there.
Yeah.
Which actually makes it harder to launch a rocket. So when you launch a rocket, there's a little bit of uncertainty in terms of where it's going to come down. And NASA likes to be very sure that it's not going to come down on a person. That's bad for, it's also bad for the, well, yeah, anyway, it's bad. There is some talk of another place in Alaska where we could launch to do this, but we would need to set up some infrastructure there in order to make it happen. So that is still something that is in the works. To be clear, the one rocket mission I described is not yet funded by NASA. It's not yet necessarily going to happen, although fingers crossed. So.
Interesting.
There's a chat question here,
Okay.
which I'll try to read for you. Mr. Bates asked the question: can local magnetic anomalies explain any of them? Perhaps they create a chaotic system that allows for phenomena deeper in space than one would think.
That was mobile magnetic phenomena, is that correct?
Local.
Local?
Yeah,
Local magnetic phenomena.
anomalies. In other words, I guess we considering distortions.
Yeah. So like I mentioned, these are highly correlated with something called magnetic substorms. And those are anomalies within the magnetic field that tend to be driven by conditions out in space and to do with the solar wind. So in general, yes, when it comes to where these parallel electric fields could be coming from, it's likely to do with what's happening out in the magnetic field. There's still a lot of modeling that has to be done to figure that out, but in general, it's how the larger system is connected that could be causing these flux. Yeah.
Well, just looking at the periodicity of the illumination and so forth, it almost looks like standing waves to me, and that suggests an RF propagation of some sort.
Right.
That's the only thing I can.
The question there is whether the instability is out in the magnetosphere or whether it's locally in the ionosphere.
Cool.
If you are gonna be ready to launch a rocket, then how long the effect lasts? So how fast you have to be to launch the rocket?
So it's going to be hard. Honestly, hitting the target is going to be the hardest part of this rocket campaign, even with the enhanced Aurora. When these appear, they can be relatively stable, although not much is known about them, so we don't know quite how stable. They will likely last for on the order of 15 minutes to an hour. When it comes to launching a rocket, we basically get the rocket ready. And then when we see it, we say, okay, start counting down. We need 2 minutes to count down. Then it launches and it takes another couple minutes to get there. So we just need it to stay. Huh? No, like 10, maybe like 10. When it comes to the picket fence, it's even harder, right? Because as you saw from the picket fence, it's on, off, on, off. And so if we happen to like go right in the right spot, but we're in one of the offs, this is what my PI would cry.
So I had a question about the challenges of sending a rocket through to measure electric field. Because if you're running a rocket through charged particles, and it's a metal object, isn't that going to generate its own magnetic field by the rocket itself going through the charged particles? Kind of like what you have when you run a metal object through an electrical thing, as an experiment.
Yeah, so in order to make those electric field measurements, we actually have instruments out on booms that are relatively far away from the rocket. And we're going to have essentially antennas on booms, multiple of them. And essentially our rocket is going to look like a porcupine. It's going to be a lot of antennas sticking out, but it should be far enough away and we should be able to account for those effects that you're talking about when we're looking at the data to try to untangle all of the effects.
So you gotta kind of figure out which part is from the, what you're actually running it through versus what is by the rocket itself.
Yes, but the rocket is a known, whereas that is an unknown, so it's, there are ways to disentangle these things. But yes, that's a good question. Other questions?
We only have any more chat.
Well, I have one. Closer to home, how does this affect radio waves? I mean, you mentioned the ionosphere and space infrastructure. Our ionosphere is responsible for skywave propagation on the ham frequencies. So I would imagine that some of this, what we're seeing here, like after a mass coronal ejection, that would impact radio waves a lot.
It can, absolutely. I mean, again, this is at latitudes where there are probably less people trying to send radio waves back and forth. But these are associated with a pretty steep drop in the density in the ionosphere, and that can interfere with radio wave propagation for sure. So, yeah, that's a good point and a good question.
Thank you.
We actually have questions on. All right, well, thank you guys, everybody, for attending.
Yep.